start recording. So if assuming this is like a notepad. I'll have like, okay, if like I will literally, I usually work in like in LaTeX. Oh, you can't see. Yeah, thank you. There we go. I will go and do this, okay? And maybe they're called something different, like problem. Instead of problem, maybe it's like solving the toughest problem in the world, you know, whatever you're doing, right? You make it more relevant for what you're doing. Introduction, data. Because usually, okay, you describe the problem. You explain the data that you're actually working with, maybe how you pre-process some of it. And then you're like, you've got some description of what algorithm you're going to use, all the bells and whistles. Usually, in computer science, we have results and discussion. Sometimes we separate these ands out into other sections, but you know, this is pretty common, right? So usually what I'll do is, first of all, starting with the intro is usually pretty tough. So I kind of like skip the intro, and I'll be like, okay, well, okay, explain. Like, let's say I'm doing TSP. I would be like, okay, is TSP. And this, okay, Hamiltonian, okay, graphs. Hamiltonian cycles, maybe about like triangle, the triangleness of like the Euclidean distance. Okay, why is it important? What have done? Yeah, like sometimes I'll have a like a lit review section where you kind of talk about what other people have done in this space, but sometimes you can kind of like throw that into one of the other sections as well. Yeah.
I'm just putting my lit review in the intro.
That's fine. That's entirely fine too. Yeah, you can make it its own thing. You can kind of like shove it in wherever it makes sense. There's no right way. I'm recording, right? Am I recording? Looks like it. Am I? Yeah. Okay. Yeah, and then okay, the data. Okay, well the data is pretty straightforward. Got it from TSP lib, cite it. But it was pre-processed by Hughes into JSON, focus on Euclid 2D problems from TSP lib. That's probably good. Maybe I can show like a show figure of a graph, I guess, like one of the smaller instances so you can kind of visualize what's going on. And maybe I can show like, maybe, you know what, while thinking about that, I go up here and I go like, hey, you know, Hamiltonian cycles, show example. Yeah, although now it makes me wonder, should I describe the data before the problem? That doesn't really make sense, but you know, it's kind of, now you can kind of see where it makes sense to talk about some things before other things. I'll have to think about that a little bit. Okay. You know what? I should also talk about, okay, yeah, down in the algorithms. Okay. It's going to be a GA, GIV over a light overview, though I don't really need to go into that much detail. It's if you're reading this, you probably know what a genetic algorithm is. You know, you just kind of hit the key points of like that loop, right? That loop, you talk about crossover. Yeah, we should talk about, okay, look, and mutation, selection. Because these are all effectively hyperparameters. They're like the symbolic ones, right? They're not the numeric ones. Whatnot. But like, what am I doing that's new? What's new? So whatever like my idea, if I'm doing TSP, I better be doing something really interesting. Like I have a new crossover. That is amazing. So I'm going to have to like describe that, right? Just explain what that is. Obviously, I'm going to explain some of the basic crossovers that I'm going to do a comparison to. Yeah. And you know what? That makes me think I should have a subsection like How will I compare, right? Like, how am I going to do this comparison, right? So I'm going to describe the algorithm, but how am I going to compare my algorithm to what's good? So do you kind of see, the point I'm making here is as I start doing the point form, it kind of turns into a bit scatterbrained. But over time, you start to go through, okay, yeah, I got to explain how, I can't forget to do that, but you know what? How will the data be stored in an adjacency matrix with the distances, like a distance matrix? So like as I'm going, I'm always thinking like, oh, I should talk about this up here, talk about that down there, as I'm going through. And chances are, you're going to want to do at least 2 passes of this, where you reread what you got and think, did I miss anything? Because you're going to think, and you're going to realize you missed things. And you just kind of go fill in the blanks. After you do this once, usually what's happened is you've kind of, like the order of these things that you add in point form might not make a lot of sense. They might be fine, but when I go through my next pass, I start to go like, okay, you know, presumably I've gone through and I've explained everything, all right? Like I've gone through and made points for all the sections, intro included. But like I'm going through and I go like, okay, tsplib, focus on that problem. You know, I should probably talk about this here, right? And okay, what is that? How is it different, right? Show a figure of a graph. You know, I could just show that. Whoops. What's going on? That's not. Apparently redo is undo, and redo is, all right. Let's see. Okay. So I'll just show the graph up here. So I kind of work on the ordering. So it's got a nice flow. Once I have the flow set, like, okay, tsplib, what's the pre-processing in JSON? How will it be stored? Maybe how it will be stored. Maybe it doesn't make sense to be in there. You know, is that really part of the algorithm? Maybe it should be. No, I like it there. You kind of create a flow, like the order in which you want to explain things. And then once you have that flow, and as you're going through and figuring out the flow, you're going to remember things you missed to talk about, so you add those points where they belong. Then you just go, like, look, show a figure. Okay, I'll find a figure. Got it from tsplib. All right, I'm going to turn this into a sentence. For TSP instances called, whatever, I'll just use Markdown. It's not going to work in LaTeX, but just, tsplib. Repository tlib. This was created in blah, 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 and holds so many instances. So you turn each point into like a sentence or so. Then once you've kind of got them into sentences, maybe they turn into paragraphs. 2 points turn into a paragraph. Maybe they are separate paragraphs. And next thing you know, you're done. Next thing you know, you've written the whole goddamn thing based on the point form. So you just turn your point form into a whole paper. That's it. That's really it. That's what I do. I wrote a book recently. This is how I did it. Like this. So it works, trust me. Okay? Cool. This works for technical writing. Technical writing is a style of writing where just tell me what you did and what happened. Don't get fancy. Everything you've learned about writing before technical writing is not helpful. I don't want any rhetoric. I don't want anything flowery. Do not put a metaphor in there unless it really makes sense for describing an idea. Keep it as straightforward as possible. It's 1 degree more formal than point form. That's really it. Cool? This works for technical writing. I don't know how well this would work for like essay writing. I've never tried. Last time I wrote an essay, I was in like grade 12, I guess, right? It's been a while. Any questions about my suggested strategy? How to write a paper by Dr. Hughes. This is how you do it. No questions? Everyone's happy with this? Who here kind of followed this strategy for their first one? Yeah? Try it for your next one. You might find it works pretty well for you. Are you doing a lecture? Wait, no. Are you doing? You are. Okay, yeah, that's not what I meant to ask. Are you working in a group for your project?
Yes.
With who? Perfect. There we go. Okay, confirmed. You still have to email me saying, I'm doing that, because otherwise I'm going to forget, and I won't get it figured out. Are you doing a presentation or just a report?
No,
for the final project. There we go. That changes everything. Shit, I got to go back and rework everything. Oh no, those dates. Oh boy. All those dates, I said pick those dates. Those might change, all because of you. This is your fault. All right. Oh man, okay. Yeah, so those dates might change a little bit. I'm still going to go on first come, first serve though. So basically anyone who hasn't picked yet, which several people haven't, they're going to get, unless you really, oh, yeah.
I emailed you back about the lecture. I don't know. You never got back to me about which one I was doing.
Oh, your topic?
Yeah.
Oh, did you change it?
Well, no, because I had artificial life. Then you told me someone else picked it.
Yeah, but I gave you back artificial life.
Oh, I do.
Oh, sorry. Did I not tell you?
No,
Sorry.
so I am doing
You're still good. You're still good.
Okay, thank you.
Yeah, yeah. That was a popular one this year. Everyone wanted to do it. And by everyone, I mean 3 people. Yeah, what am I going to do with those presentations? Because if you're giving a presentation, I want to give you a full lecture to do a presentation. You don't need to take the full time, but you'd probably be surprised at how long you can talk about what you're doing. So that means, like, the day, let me ask you this. The day after X-Ring, which is the 4th, I think. What does that mean? You don't want to do it that day? Yeah, no, no one knows. Okay. Huh. That's a Wednesday, though, and that means the lecture would be at 10:30, not 8:30. Remember that. You're still like, no, okay. All right. Ah, shit. So that means I would need to do the Friday. The Friday. What if, how would you feel if, and I'm going to pause the recording temporarily. Because I don't want anyone to, hold on. We'll be right back. Okay, and we're back after we've changed everything. Okay, so we're not learning about exceptions. CSCI 340. We are comparing distributions. So what does it all mean? This is a big one. Whenever we get something like, on average, my algorithm's better. An average is a statistic. It's a statistic that's trying to summarize a lot of information. But, like, look, if I hit run on an algorithm, do I get the same result every time if it's a GA? No. If I hit run and I keep hitting run, hopefully I get similar-ish results, maybe not even, but if I hit run a bunch of times, I'm going to get a suite of answers. Sometimes it does better, sometimes it does worse. You know, if I keep doing it and I plot it as a histogram, I might get like a nice distribution or something, right? And when I calculate the mean, or the median, I'm just getting one number that's trying to summarize all of that information, which is, of course, like great and all, but it's only one piece of information. If I try to compare means, like what I really want to do is compare how every time I hit run, I get a slightly different result, but I want to compare these algorithms. And by hitting run a bunch of times and getting means and being like, oh, this one was better, you're being unfair. That's not a good comparison. You're using a proxy summary statistic and another proxy summary statistic to compare two things that are not the summary statistics. At best, you could say the summary statistics are different. Yeah, fine, but no one cares because the point of that statistic is to tell you something about the distribution. So, random variables. Before anything though, I'm going to keep this topic at a high level. If you have a really good stats and probability background, you're in great shape. You know this stuff already. Great. But I'm going to keep this at a high level. I'm going to skip the formalisms. What I'm going to do is try to give you the intuition about what the hell we're doing and why we're actually doing it. A lot of people, myself included, when I learned all this stuff, I was taught terribly. People explain this really badly to me, and I never made sense. It never really made sense. I just knew, oh, to compare these things, I just run it through these functions and I get an answer in the end. And you ask me, what does it mean? I can bullshit some answer, but I didn't really know. Because it was very poorly explained. And I think it comes down to a lot of people don't really understand it. Honestly, I think most of your computer science professors don't actually understand this shit. They're just telling you what they were told. So my point, what I want to do is I want to give you the intuition as to what we're doing, why we're doing it, and what it really means. What we're saying when we compare our distributions. So, first, I want to show you how do we actually compare your algorithms. And then I want to give you the intuition as to why we do it that way. Okay. Consider a random variable. If you've taken stats, you've seen this word before. A random variable. Now, the word random variable, if you're a computer scientist, sounds like a bit of a misnomer. A variable? Well, it's not quite like a variable like how we're used to it. A random variable is a well-defined term in statistics. It's something that we can go and we can observe, and every time we observe it, we might get a slightly different result because we're measuring some natural phenomenon, and it's always messy and noisy data. So we're going to go observe some random variable, some quantitative measurement that I can take. It could be something like the time it takes to recover from the flu, right? I get everyone in this room sick, and I measure, okay, how long did he take? How long did he take? How long did he take? And I can take all that data down. Or maybe it's the amount of nuts an individual squirrel buries on a given day. On Wednesdays, he seems to bury a lot more, right? Did everyone hear about Peanut? Oh boy. I know. I don't want to break it to you. Peanut. The number of people with blonde hair that walk by this building between 10 and 11 a.m. on Tuesdays. I can measure that as my random variable. And the best fitness value of a genetic algorithm run. Every time I hit run, I get a different answer. I shouldn't have brought up Peanut. Yeah. It's a sad story. It's a sad story. It'll make you mad. Apparently, it had an impact on the election. I'm so confused. I don't know. That's what people are saying. Never mind. Anyways.
Oh, I did see that.
You did see that? Yeah, what's up with that, right? So, okay. Here's what we have. I have two random variables. Here's one. I'm going to think of this random variable as an abstract thing. It's this box. Now, that box is representing nuts buried by a squirrel, days it takes to recover from the flu, genetic algorithm runs. I don't know. It doesn't matter. I'm just thinking of it as a box. So I've got this box on my desk, and it keeps spitting out numbers. The first number is 15, 19.5, 15 point. I keep doing that, and I observe it longer and longer and longer and longer and longer. And I keep collecting more and more data, and eventually I get a histogram that looks like this. A histogram is effectively just a bar chart that is showing, we usually come up with these things called bins, okay? And we say, well, how many observations, when I'm observing this random variable, how many of the observations, we've got a count, and here we've got the value of the observation. So here, it looks like I have one measurement at 10. Here I've got, well, actually it's hard to tell based on the x-axis how many. But the bins Oh, you're learning about Peanut, aren't you? I know. Like, why did they do that to Peanut, right? Like, what's going on?
This is like really high quality journalism for like a dead school. It's insane.
It's the best quality journalism you get these days, right? Yeah. Yeah, man, yeah. So, point being, I've ruined today's lecture now. I'm just talking about, this is what killed it. I've got a histogram. These bins will be like, okay, how many did I have between the value of like these are floating point numbers to 1 decimal, okay? So how many observations did I have between, this looks like it's probably like 9 and 11, I don't know, okay? There was 1, it looks like. And then between 11 and 13, I don't know. Right? That's how many observations I had in that. So I get a histogram like this. So we can see what the histogram is telling us is like the frequency of each observation. And we can see, well, the majority of the observations were like here, right? And then like, you can kind of think like it's mostly here. We have few out here, but a lot more here. Meaning that like, well, I mean, if we were to take an average of this, obviously the average, the mean, would be somewhere around here, right? But that's just a summary statistic of this distribution. What I really care about is the distribution of the data I got from my random variable. Cool? Cool. Now, here's another random variable, okay? It's a slightly different color. This one's dark gray, this one's light gray, and it spits out data. And I go observe it for a time too, and this is the distribution I get. Looks a little bit more messy, but that happens with data. So the question I'm now wondering is, and now remember, this box is simply a stand-in for some observation. The number of nuts, the number of, one algorithm I was running generated these results every time I hit run. And another algorithm I was running, I made some changes and I kept hitting run on the new instance. I kept hitting run and I got these results, right? Now the question is, are they different? Did one algorithm perform the same or different than the other algorithm? That's the question I have. If I were to go and take the averages, I think I have, no, I don't have them listed here. If I were to go, 50 data points are shown, 50 data points are shown. If I were to take the averages, chances are the averages would be different. But like, I've got my base genetic algorithm, and then I implemented my own new crossover. And I'm like, it's better. And I hit run, and I got these results. So the question now is, so is it? Is it actually better? Well, how do I know? Well, let's find out. Or did it make no difference? Like, is this distribution effectively the same? Like if this distribution came out of this box, if I kept observing this box, could that box have generated this distribution pretty easily? That's the question I'm trying to figure out. Is the distribution that one box produced actually different than another distribution, another box's distribution? So regardless of what the random variables are, one may wonder, are these random variables actually different? If considering the flu recovery time, the random variable may be recovery time of two groups of people. Does one group recover faster? Does a group I gave some drug to heal faster than a group I didn't, for example? With the squirrel, does one squirrel bury more nuts in a day than the other? Does 1 year have more blonde people walking past Mulrooney on Tuesday from 10 to 11? It can be whatever we want it to be. That's what's beautiful about the statistics is it's so abstract, you just apply whatever you want. Does one evolutionary computation algorithm implementation perform better than another? Those are the questions that we can try to answer with the following. So here's what I've done. I've shown, okay, this is the distribution, this is the distribution. These are the distributions plotted on top of each other. Are they different? It's kind of hard to tell, Remember, when I'm asking different, I'm not saying, are they different? Because you could be like, one's orange and one's blue. Yeah, obviously. One's a little bit more this way than that one. The blue one's clearly a little bit more this way. The orange one's a little bit more this way. They're different. Are they, though? Because these are random variables. It's possible that I delete this histogram and I just start observing 50 new data points from this one. The distribution I get is going to be different. Every time we hit run, we get a little bit of a different result, right? So, is it reasonable that this histogram could have been generated by this random variable? Or is it actually more likely like, no, they're actually different. It's likely that they're different. That's the question I'm trying to answer. Is it clear? This is the complexity. Now, at this point, well here, let me make sure I'm actually at the point I want to, okay. When visually analyzing the comparison of the two random variables, there does appear to be a difference, but the data is clearly noisy. A range of values are obtained for each random variable, and there are only 50 observations of each random variable. That's not a lot, actually. It's difficult to say if these random variables are truly producing different distributions, different sets of data. They may effectively be the same. They might not be. They might be different. The two groups do not take, if we're talking about like, did the drug work? The two groups do not take different amounts of time to recover from the flu. One squirrel didn't bury more nuts than the other. And there really isn't more blonde people this year versus last people. My algorithm isn't actually outperforming the other one. It's performing basically the same. This is what I want to know. Is it or is it not different? At this stage, you may be thinking to yourself, okay, I remember, you might be thinking to yourself a few things. You might be thinking, yeah, how would you compare that? I don't know. Turns out the way we ought to do this is really simple, and it makes perfect goddamn intuitive sense if you follow along and you listen carefully. There's no logical leaps you have to make. Everything makes perfect sense, and it's infuriating to me that you don't know this, and it's not your fault that you don't know this. I want to be very clear about that. It's not your fault. Whoever's taught you this shit, how they got away with not showing it to you is mind-boggling to me. So don't worry, I'm going to make it make sense to you. Not today, unfortunately, we're running out of time. The other group of you might be like, oh, I know, you throw that into like a t-test, and you get your p-value, and that's what you do. Who here thought that? One person? Yeah, right, 2 people? Yeah, that's what you're supposed to do. Okay, that's great and all, but the problem with that is, do you know what that t-test is really telling you? And did you know that that t-test is actually like a mathematical hack that requires several assumptions to do what we actually ought to do in a quick and dirty way? You know, a lot of the statistics that you learn are based on courses that were designed 100 years ago. They're like the t-test, I'm pretty sure it was the t-test, was invented by a guy at Guinness Brewing Company, by the way, as a way to like do a comparison of something. Because we all know the right way to compare distributions, which is the way I'm going to show you, but it takes too long if you're working with pencil and paper. Fortunately, for a little while now, we have computers that make it trivial to do it. We don't need pencil paper. Yet we're still teaching people the quick and dirty way to do it as if we didn't have computers to do all this calculations for us. It's weird. So the t-test is a quick and dirty way to give you like an approximation for what we really want to do. Really what we want to do is like our permutation test, which we're going to talk about Friday, I guess. And we're going to talk about that in the context of a very commonly used example, a drug trial. I'll tease it for you today and we'll finish it off on Friday. Consider a drug trial. A group of 50 people is given a new drug that is intended to reduce the time of the flu. Another group is given a placebo. This is a common like double-blind test trial thing where people are given a placebo so they don't know if they have the drug or not, because turns out placebos actually can have a big positive effect on you. And that's an important thing about placebos, by the way. People think like, oh, it's the placebo effect. It does nothing. No, the placebo effect actually does have like a physiological positive effect, which is weird, but it works. It means I can give you snake oil and tell you it'll cure your arthritis, and you'll be like, shit, it kind of does. And you actually feel better. It's weird. So That's why a placebo is always kind of there. And the double blind is the fact that the people doing the research don't actually know up front who's in what group. So everyone's a mystery, and then they do the calculations, and they'll go like, I think it's this, and then they can confirm it based on what was going on. Anyways, this is a common thing. Another group is given a placebo. No one in either group knows if they are given the new drug or the placebo. Here, the random variable are the two groups of people. Recovery time of people that were given the placebo, and the recovery time of the people that were given the new fancy drug. It's the random variable. This is the property characteristic trying to be understood. Cool. And we'll stop here, and we'll see y'all Friday, and you're going to get a bunch of confusing emails from me outlining what you made me do today.
So sorry.
Yep, it's your fault specifically.
Oh.